This video is an introduction to Gauss's law of electricity and magnetism. Let's say we have a charged sphere, a charged conducting sphere, where the charge is uniformly distributed, and I would like to find the electric field at some point outside that conducting sphere. So by symmetry, we know that this electric field at that point, to make it closer, the electric field at that point will be radially away due to the symmetry of the problem. And at all points basically, which are at the same distance from the center, the electric field is going to be pointing radially away, having the same magnitude, simply because they are all at the same, those points are all at the same distance from the center. So, to find the electric field at that point, we will draw what we call by a Gaussian surface that passes through that point. That's a Gaussian surface that passes through that point, that is concentric with the conducting sphere. And because it's a Gaussian surface, I'm gonna put dotted line, which means it's an imaginary surface. So that surface, we call it a spherical Gaussian surface. A spherical Gaussian surface. Now, at any point on that surface, at any point, the electric field will be pointing radially outward, and all of those electric fields are going to have the same magnitude E. Now we apply Gauss's law. Gauss's law states that the flux through a closed surface, which can be represented as E multiplied by dA, is equal to the charge inside that Gaussian surface, Q enclosed, over epsilon 0. Now, we can notice that for every dA here, for every small dA, I have the normal to that area is in the same direction as E. Everywhere, the normal is in the same direction as E. So E dot dA becomes E multiplied by this dA multiplied by cosine 0, which is 1, because the angle between E and the normal, this is the normal, between E and the normal is 0. So cosine 0 is 1. Closed integral of E dot dA, it's a Q enclosed. This Q enclosed, it is simply the charge of that conducting sphere, because the whole sphere is inside that Gaussian surface over epsilon 0. Now, since E is constant, that's the whole idea. We are taking a surface where E will be uniform or has the same magnitude everywhere along that surface, so that I can take it outside the integral. So that's the whole point of Gauss's law, using Gauss's law to take E outside the integral. What's left inside the integral, it's dA. And integral of dA is simply the area of that Gaussian surface. What's the area of that Gaussian surface? It's simply 4 pi r squared, where r is the distance from the center. So let's draw this r. It's from the center to that Gaussian surface. This is r. This is r. 4 pi r squared is Q enclosed, or Q in that case, over epsilon 0. So E becomes Q over 4 pi epsilon 0 r squared, which is KQ over r squared. And that's why we say that the conducting sphere, behaves as a pointed charge when we want to find the electric field outside it. All right, let's take another example. Let's say we have an infinite sheet a charged infinite sheet, a very large sheet, which means I want to find the electric field very close to it, so it appears to be infinite. And let's make it easier for us and make it positively charged again, uniformly distributed charged. So that's an infinite sheet. Okay, infinite sheet. So again, by symmetry, the electric field is going to be pointing outwards and has the same value everywhere. Everywhere this electric field is gonna have the same value, because we are considering this infinite sheet, or this sheet, to be infinite. So all the electric field are going to be having the same magnitude everywhere close to it, so that it appeared to those points to be infinite. So to find that electric field, I will take again a Gaussian surface. And in that case, I want to choose a Gaussian surface where I can take the electric field outside the integral. So the best choice will be simply a cylindrical Gaussian surface. Okay, that's a cylindrical Gaussian surface. Let me draw it in a good way. Okay. So that's the cylindrical Gaussian surface, and let's write beside it cylindrical Gaussian surface. Cylindrical Gaussian surface. Okay, clearly we can notice that the electric field, let's remove those. So you can see how the electric field looks like on that surface. So that's the electric field. Here I have electric field. All of those electric fields have same value. All of them have the same value. Now I use Gauss's law. So the closed integral of E dot dA is Q enclosed over epsilon 0. Now again, you can see that electric field and the normal to that surface, that's the normal to the surface, all of them have the same direction. So cosine 0 is 1. And E is uniform again along that surface. So I take E outside. Integral of dA, we can see that the electric field is only passing through the top surface and the bottom one. So if I consider the area, the yellow area is A, so how many areas I have? One on the top, one on the bottom. So it's 2 multiplied by A. Q enclosed, it is the charge here. It is simply the charge in that part. And the charge in that part is equal to the sigma, which is the surface charge density, multiplied by the same yellow area, A. Q is sigma multiplied by A, over epsilon 0. So E becomes A and A cancel, so it becomes sigma over 2 epsilon 0. Again, we can see clearly that this electric field doesn't depend on the distance away from the sheet, because this sheet is considered to be infinite. So the points do not recognize how far they are from that sheet. So this is how we use Gauss's law to find the electric field of an infinite sheet and of a sphere. Thank you for watching.